So we've now got, we're going to include symmetry in the picture. So I'm going to have to talk a bit about what symmetry means. So we have some group of transformations so if we come back to the two formulations at the beginning, classically they were called canonical transformations. Equals transformations preserving the form of Hamilton's equations. So you do some change of coordinates, and when you look in this transformed coordinates, your equations of motion will have the same form as Hamilton's equations. So you'll have some new Q's and new P's that might mix the Q's and P's up. But the equations of motion will still be Hamilton's equations. The transformed equations of motion will still look like Hamilton's equations, this special form. Or in modern language, the symplectic transformations. G is some diffeomorphism of the manifold. Which means that such that it preserves the symplectic form. And then when it preserves the symplectic form, it will also map the Hamiltonian to some new Hamiltonian function in new coordinates, but it'll also map the vector field to the vector field, because the vector field is determined by the Hamiltonian and the symplectic form. So I'm not going to talk about anything global for the moment. I'm just going to talk about local, again, near equilibrium points. G acts linearly on, so that means that each element of the group, so the group might be finite or not finite, group of rotations in Rn, for example, or something like that. Or it might be a finite group, like permuting the coordinates, Q1 and Q2 swap. Something like that. So finite or not finite. So this means that so each G is a 2n by 2n matrix. And in particular, it has to be what's called a symplectic matrix. So this means where J was the matrix we had earlier. So that's the equation you need to satisfy in order to preserve the form of Hamilton's equations, because that was the crucial the crucial ingredient. That took the place of the symplectic form in Hamilton's equations, this matrix J. So we write it's the group of symplectic matrices with real coefficients. So this is a symplectic representation. So that's just means the same thing. So there's there are three types of symplectic representation. Oh, let's just say example. General example. So if A is any n by n invertible matrix, then that matrix, this is the inverse transpose matrix, is satisfies this. And that's the typical sort of matrix one obtains from such these symplectic symmetries. So that means any, so usually you would think of A as being an orthogonal matrix, because there's some geometry involved as well. Then A inverse transpose is the same as A, so it's just two copies of the same matrix. So, when we want to understand symplectic representations to understand symmetry, we need to know what the building blocks of these things are. So these are built out of irreducible representations. So let's call this representation, this vector space V. If there does not exist a G-invariant proper symplectic subspace of V. So the only invariant subspaces, symplectic invariant subspaces, are the whole space and 0. So if we ignore the word symplectic, there are two types of irreducible representation over the reals. In complex, there's sort of one type, but no, what am I saying? There are three types. In general, there are three types of irreducible First one is called the real type, and V is the direct sum of two representations I'll give examples of each of these in a minute. So W is, and I'll say what absolutely irreducible means in a moment, with going to this splitting minus J has that form. So that means that with J, which is the symplectic structure, you can't separate these two W's because it mixes them up. That's one to the other. So as a whole, it's symplectic. So if you've seen any representation theory before, this might be familiar. So it means what? It means that the set of let's give it a name. Hom L.G. So the only commuting, well, that's right, it's equal to R times. So G equivariant means commuting with G. So when you study representations or dynamics with symmetry, linear dynamics at least, then it's very important to understand the set of maps which commute with the, because the symmetry is a linear vector field is symmetry if the matrix L commutes with the G, with the group. So it's important to know what the set of linear maps are that commute with G. So here, on W, this summand, Lg, anything that commutes is just a scalar multiple of the identity. So in this case, L is so it's just copies of the identity matrix. There's no other way an element can commute with the symmetry. So that's the first type. Oh, and I should say, and L is Hamiltonian. L is a bit like I'm going to change the so I'm using the same letters A, B, and C as I had when I was talking about this case. So we can see that it's very similar to just in the two-dimensional case, what we were talking about before. Oh, I've got my C and my A the wrong way around. Let's put C here, minus A.
So, LG, what is LG? So, bilinear form, G invariant bilinear form?
What is, sorry, what?
LG.
Oh, it's the set of all, it's this.
Definition.
Yes, yes, sorry, yeah. So linear maps from W to W that commute with G. So that's the first type. Complex type, there are three types. So V doesn't split up into anything. So V is itself irreducible. Here V was not irreducible. It was irreducible as a symplectic when you take the symplectic structure or the matrix J into account. But if you forget J, it splits up into two. This one does not. And L, G, B, V, well, it's isomorphic to the complex numbers, which is why it's called complex type. And 3, what do we write as the quaternions? H. So if we forget about symplectic, so if you've studied any representation theory, then you'd know that over the complex numbers, if you have a complex representation, which is what most people write about in representation theory because it's the most beautiful subject, I think, complex representations, and it's very, in a sense, it's very simple, and it's very uniform. It's not simple, but there's only one type of complex irreducible representation over the complex numbers, and they always satisfy this for an irreducible representation. Over the reals, there are three types. One has this property, So the set of commuting linear maps, so if it's a linear map and it commutes with the group, then the kernel is invariant because the matrix is symmetric. So the kernel is invariant. So if the kernel is not 0, then it must be an irreducible, it must be some subspace which is invariant. So that tells us that the set of, if the space is irreducible, the set of commuting linear maps, every map in there is invertible, apart from 0. So there's 0, and there's all the invertible matrices. So that's what in algebra is called a division algebra. And it's a famous classical theorem that there are 3 division algebras over the real numbers. Over the complex numbers, there's only 1, which is C. And over the reals, there are 3. There's the reals, the complex numbers, and the quaternions. So this gives you 3 types. But if you take the usual representation theory knowledge, there are the 3 types. There's the real type, but the real type can't be symplectic on its own. Just W is cannot be symplectic. There's no J like this on W, because the only things that commute are multiples of the identity, and that J is different. So it has to be 2 copies. Otherwise, it's the same as here. Of course, this looks like C. So there is some matrix in here whose square is -1, right? So J the matrix J is whatever it is that maps to I, or minus I. Okay, so because J squared is -1, that was one of the properties of J. And here, there are lots of matrices whose square is minus the identity, or -1. Lots of elements of the quaternions. There's a whole 2-sphere. Here there are just 2 elements. There's plus or minus I. Here there's a whole load of them. But anyway, any one of those will do to be the matrix J. So we have these 3 types of representation. So let's just see a couple of examples. Now let's start with complex. So R2 is symplectic. With that matrix J. And the rotation, this matrix, if we think of it geometrically, it's a rotation by pi over 2. So obviously it commutes with all the other rotations. SO2 is the group of rotations in the plane. And rotations all commute in the plane, not in 3 dimensions, but in the plane. So this and this, they commute. So if I think of this R2 as a complex plane, then SO2 is what's often called U1, so it's the set of rotation is just multiplication by e to the I theta. It's a rotation through theta. And what transformations of C commute with e to the I theta? Well, it's just the rotations and the dilations. Reflections don't. Reflections and rotations don't commute. So it's just scalar multiplication. That's typical example of complex representation. Cyclic subgroup of rotations a group of order n. It's just a subgroup of SO2. Some people write Cn, some people write Zn. So that's the same type. For n bigger than 2. Quaternionic, in a sense, there's only one example. Well, it's not true. G is SU2 in 4 dimensions. So the only things that commute with that are, so we can realize SU2 as quaternions, also, unit quaternions. So I'm going to identify this with the quaternions, and then it's the same argument as before, except we have to be careful with quaternions. But this is a bit of a digression, but let me just finish it because it's one of the 3 cases. Set of linear maps so if we take an element of SU2 is multiplication by unit quaternion on the left. So in quaternions, multiplication on the left and on the right are different. It's not commutative algebra. I don't want to spend time on this example because it's not going to come up again. It was just for completeness. So then L, G, H consists of multiplication by quaternions on the left. That was the left. On the right. Because multiplication on the left and on the right commute because of associativity. These are associative. Okay, so you can look it up. Or ask me questions afterwards. In a real case, which is more interesting, well, the simplest Z2 on R2 by, so how's Z2 acting? By minus the identity. then R2 is R plus R. So that's this type here. And of course, R is irreducible. And here, the Z2 is -1 and -1. Right? Not so interesting. Better example is Dn, or so the dihedral group, which is rotations and reflections in R2, or O2, O2 is rotations in the plane and reflections. So this is just similar to this first one. Here we had SO2 on R2, and now we've got O2. Here we have the cyclic group, which is just the rotations, and now I'm including the reflections. So the dihedral group is something like symmetries of the hexagon. In this case, with sort of Dn acting on both copies. So again, this is for n and bigger than 2. Yeah. So if A is in Dn, then G is A, 0, 0. And here I had A inverse transpose, but it's the same because A is an orthogonal matrix. So that's the typical sort of representation that one gets in the reals. There are other examples, but this is the one we're going to talk about in examples. So, what's the point of all this? Theorem of Golubitzky and Stewart, 1986, was the first to study this general question of bifurcations in Hamiltonian systems with symmetry. They had already studied bifurcations in general dynamical systems, not Hamiltonian, a few years earlier. You might have seen the big books on bifurcation theory by Golubitzky and Schaefer, and Golubitzky, Stewart, and Schaefer. So in there is where they work out all the representation theory needed for the for bifurcation theory in general, and then this was the beginning of the Hamiltonian case. L, so now I'm going to have lambda. So linear Hamiltonian systems. So we've got a fixed matrix J, which is the symplectic structure, or the structure of Hamilton's equations. So J L lambda is J times S lambda. So S lambda is a one-parameter family of symmetric matrices. So we want to repeat what I was saying about bifurcations in the plane, where we had that picture of the cone. So what's the relevant one? So commuting with a representation of a, well, compact, so it could be finite group G on some vector space V. Then generically, so like we had before with the cone, generically a path will meet the cone at some non-zero point, but some special things might occur where it's here, but generically it'll be in the meet the cone. So it's that sort of generic, you can choose your path generically. A bifurcation occurs at lambda 0, or lambda equals lambda 0, where L lambda 0 has a 0 eigenvalue. Of course, that's where bifurcations happen. Yeah, but not the only one. And the 0 generalized eigenspace is symplectic. So generalized means you take powers of L in case they're a nilpotent part. So it's symplectic, or is a symplectic irreducible subspace. Let me call it V0 of V. So generically it's irreducible. And there are two cases. If V naught is of real type, right? So that's this. V is splits as sum of two parts. Then L naught is nilpotent. Not 0. And get a splitting of the eigenvalues. In one direction or the other, depending if you're increasing or decreasing lambda. It doesn't matter. Right? So on one side they're imaginary, go through the bifurcation point. On the other side they're real. So if V naught is of one of the other two types, then L naught is 0. And the eigenvalues behave differently. Or possibly the, no. Can they be real? No, they can't be real. So you get the passing like this. If they were real, you'd have a real eigenspace, and that would be contradictory to having complex type. So the type of representation is reflected in the type of behavior you get for the eigenvalues. So what does this mean? So here, if this is imaginary, which might mean that because the system is stable, when you have stable eigenvalues, stable equilibrium, the eigenvalues are all imaginary. So this could be from stability question. Here it's definitely unstable. You have a saddle point, like I drew early on. Whereas here, it's quite interesting, you get stability of some sort, at least at the linear level, stability on both sides of the equilibrium point. Okay, so perhaps that's the time to stop for the moment. So the message there is that the symmetry influences the type of bifurcations that can occur. So maybe I should stop there for lunch, and then afternoon I'll talk about some actual examples where these things arise, and we'll see some. And I'll also talk about part 3, which was about reduction. Okay? Any questions? No? Okay.
So is the afternoon lecture will start at 1:30?
1:30? Yeah. Oh, yeah. I've got 12:30. I've only spent half an hour. Maybe I should continue.
Oh, sure.
I've forgotten the time.
10 minutes.
Sorry?
You should have a 10 minutes. 10 minutes or.
Shall I continue?
You sure?
Yeah, okay. Sorry. I forgot what time. Yeah. Confusing to see if I've watched anything recorded yet. Yeah, so we'll continue my mistake. So in case 1, the bifurcation picture is the same as the one for R2. L lambda is something like, where have I got it written down? Up there. Yeah, and degenerate when b squared equals AC, and one has a curve that goes through the cone like that, one way or the other, which explains these passing, splitting. So there's one other interesting case of bifurcation. And this is where we start with imaginary eigenvalues, and then they move out into the complex plane. But how can that happen? So, if we have a pair of simple eigenvalues, so in generic dynamical systems, that can happen. The eigenvalues just move off the imaginary axis. But in a Hamiltonian one, this can't happen. My dilemma above about the eigenvalues. But what can and does happen is a very interesting bifurcation. Where you have 4 eigenvalues. So this must be in at least R4. And as lambda as lambda varies, these move together. So they move together, and now they can, because they're not single eigenvalues. So they were simple ones to begin with, then they collide, and then they can move off. So this is called Hamiltonian Hopf bifurcation, and it has some interesting dynamical questions occur, which I'm going to talk about in a minute, or no, later. So in a symmetric system, this happens just without any symmetries. It's what often happens. I have to say something about an important condition on this. But in a symmetric system, there is a similar genericity statement about types of representation involved. I'm not going to go into the details. All right, it's complex type or something else. So this is a theorem due to leave it like that. Well, V naught, that's the representation. Well, it's not V naught anymore because the eigenvalues, but V, let's say, oh, I don't know. Let's call it V0 anyway. V0 must be a sum of two copies of isomorphic representations. So either in the real case, like V is W plus W, or two complex ones or two quaternionic ones. Theorem of Delmitz and Melbourne, I think, 1992. And one gets this sort of picture again. So there's an important condition that I haven't discussed. Something often called the Krein so this is first developed in the 1950s by a Russian mathematician M.G. Krein. I'm just trying to remember which way, how best to say it. Oh, we go. So if we have a pair of conjugate eigenvalues, simple ones, plus or minus I omega, then of L, then there is a real, so L is some maybe high dimensional system, 2n by 2n, but I've got a pair of simple imaginary eigenvalues. Then there is a real eigenspace corresponding to with, let's call them eigenvectors. So one can go through the best way to prove all this is to complexify the matrix and look at the complex eigenvectors, complex eigenvalues. Let's call them psi and eta. It's a two-dimensional thing, so we've got a pair of vector fields where L psi is omega eta, and L eta is minus omega psi. Okay, so we can always choose a psi and an eta such that that's the case. So the psi is an eigenvector of L squared with eigenvalue minus omega squared. And that's why you get plus or minus I omega. And the sign so if we put psi transpose j eta, that's a convention. You could put eta psi the other way around, but that's not the same. That'll have the opposite sign because J is skew-symmetric matrix. But I've chosen psi and eta by this. If I chose eta and psi the other way around, I would have the minus sign here. So that determines which is psi and which is eta. And this Krein proved this is well defined. He didn't write it exactly like this, but that's what it comes down to. So when I come back to talking about the Hamiltonian again, we'll see where this comes from. The Hamiltonian Hopf can only occur if, so we have at the beginning, where's it gone? Over here. We have two separate imaginary eigenvalues, so let's call this I omega 1, I omega 2, like that. If the sign of in this sense, the Krein, let's call it the Krein sign like this, so the Krein sign of the two are opposite. So one is positive and the other is negative. If they have the same signs, then generically they do not collide. So what happens if you do have a one-parameter family where this happens, they can't bifurcate off. They have to stay on the imaginary axis. But if you perturb this family, they would do this. They wouldn't meet. And it's a similar analysis as this one. It's a curve. The collision would happen here, but there's no reason that the curve would have to go through there. If you perturb it a bit, it hits somewhere else. It's a different analysis. I mean, it's not coming from a matrix like this, but it's the same picture in the end. This was first, I think this was in a paper of Mackay. Robert Mackay in 1986, who was the first who understood what this analysis here. He says it was due to Krein, but Krein didn't talk about this case. And again, with symmetry, so that symmetry means you have multiple eigenvalues. We'll see this in more detail this afternoon. So symmetry, the group forces eigenvalues to be multiple, so you can't have simple ones anymore. But you can have them as simple as possible, compatible with the group. So this means the eigenspace is symplectic irreducible, like we had earlier. Then Krein sign is well defined. And again, Hamiltonian Hopf can only occur for opposite signs. But with symmetry, passing can occur generically. And to my knowledge, nobody has analyzed satisfactorily what happens in those cases for the nonlinear dynamics. For the linear one, it's clear, but for the nonlinear, it's not. So that's all rather sort of lots of theorems of the structure of the problem without any examples or real insight into dynamics. So maybe I'll stop there, and then this afternoon I'll talk about more about the dynamics and what actually happens. Periodic orbits near equilibrium points and so on. Okay, so now I will stop. Any questions?
Krein sign is not limited to the Hamiltonian. Any.
Well, this matrix J is what makes it Hamiltonian. Yeah. And this form of the equations as well is Hamiltonian. Okay. Any other questions? Okay.